Right. Hi everyone, I'm Nicolas. I'm a software engineer at Meta in the PyTorch team in London. I usually work on Torch Vision. I've been maintaining and developing Torch Vision for the past few years. And these days I've been working on TorchCodec, which is the new media decoding library for PyTorch. I'll be talking about that today. So TorchCodec is a PyTorch library. It's about decoding and encoding. For now we only support decoding, but encoding is in the works. It's about decoding video and audio data. So you feed TorchCodec a video file or some audio from the web, a URL or anything, and you get a nice decoded PyTorch tensor as output. We do that on CPU. We also support GPU as well. So we have this GitHub repo that you can check out if you want. We want to be easy to use. We target machine learning engineers. We don't want our users to know anything about how decoding works. We just want you to get the data that you want as easily as possible. We want to be easy to install, which is a very important requirement for us. You might know that there are some video decoders in Torch Vision, for example, that are not necessarily easy to install because you have to build from source and things like that. So we avoid that in TorchCodec. You can just pip install TorchCodec, and it's going to work with the FFmpeg binary that you have on your phone. And we want it to be fast, and we want it to be integrated with the ecosystem as well. And that means that the output that you get from TorchCodec is the input that you can feed to other libraries like Torch Vision or Torch Audio to transform these video frames. So as soon as you get the encoded frames from TorchCodec, you can transform them with Torch Vision without having to do any kind of pre-processing or anything like that. So we wrap around FFmpeg. FFmpeg is this low-level library for video decoding. It's very hard to use and very complex. We abstract that complexity from it, that you can just have a nice Pythonic interface to deal with when you're building your models. So we'll be looking at some code. I'll basically just show you a few snippets of code to explain the different features and what you can do with TorchCodec. Everything we'll see is also on our tutorials online, so feel free to check them out as well. Okay, so I hope you can see the back. The main thing you will be interacting with when you're using TorchCodec for video decoding is this video decoder object here that you can just instantiate by passing it a video file. It can be a URL. It can be raw bytes, the raw encoded bytes of the video, and it can also be more complex than that we'll get into. You can ask for the decoding to happen on CPU or on CUDA as well. You can pass a Torch device like CUDA or 0, that kind of stuff. It's going to work on GPUs. So here I'm just giving an example of instantiating such objects, and we're getting the metadata from it. The metadata is a bunch of information that is contained in the header of the video, for example, but it can also be some information that we, TorchCodec, compute ourselves and give you a more accurate representation of. So the headers in the videos sometimes are not always accurate. They can be lying, they can be wrong, or they can be missing or corrupted or any kind of stuff. So sometimes the header will tell you, hey, you have 400 frames in that video and you actually have 399. So we do some kind of pre-processing in the video to show you exactly the accurate information. I'll talk more about this later. Once you have instantiated a video decoder, you can get the frames by just indexing the actual decoder object. So it works just like as if it were a list. You can use simple indexing or like slices and that kind of stuff. What you get as output when you index the decoder or when you iterate over it, like at the bottom, is a pure tensor. So you get a pure tensor of UID8 values, which are just the pixel values, and the shape is just number of channel and then heights and width. You can get the channels at the end if you want to. That's just a parameter that you would pass to the decoder if you need them to be channels last. So you can index the decoder like I just described, but if you want more information about the frames, you can use the methods that we provide. So here, the first method we're using is getFrameAt index 0, so get the first frame. And what you get is not a pure tensor, it's a frame object, which is just a data class that has a data field. The data is the actual tensor data. And then it also tells you the PTS. The PTS is the presentation timestamp. It's where the frame is first displayed. Here it's 0 because it's the first frame. It's second 0, and the duration of the frame. So yeah, you get a little bit more information when doing that. If you need to decode multiple frames, just a performance tip, do not call this function on different indices. We have a method specifically made for decoding multiple indices at once, which is get frames at. What you get as output is a frame batch, so it's basically the same as the frame object, but it's the batched version of that. So instead of, for example, PTS happens to be a single float, it's going to be a tensor of as many frames as there are in the batch. The reason this method is faster than calling the individual frames is that we are pre-allocating the data, if we can, and we are also sorting the indices so that you never have to do any kind of backward seeks, because backward seeking tend to be pretty slow when we're decoding. So here I'm presenting index-based API where we are asking for the first frame or the second frame or the last frame. Sometimes you want time-based APIs. You want like the frames that are displayed between the first seconds and the 5th second or stuff like that. So we also provide these time-based APIs. They work exactly the same as the index-based one. I'm not going to detail them, but they exist. We have that symmetry in the APIs that we offer. Clip sampling. So when you're building or training a machine learning model, sometimes you don't want to pass a single frame to the model. You want to pass a sequence of frames that are ordered in time. And here I'm just going to be calling that a clip. So a clip is just a sequence of frames. They're not necessarily contiguous, but they are ordered in time. And so so this you can think of it as just like a short video. And sometimes you want the frames to be spaced by a given amount of time or a given amount of indices, and you want to specify that you have like X frames per clip. So you can do that very easily with TorchCodec. Here I'm just asking for clips at random timestamps, so the timestamps are going to start randomly. I'm asking for 3 clips, 2 frames per clip, and 3 seconds between each frames of each clip. And what I get as output is a frame batch as well. The dimensions are that, like the first dimension is 3, that's the number of clips we ask for. 2 is the number of frames per clip, and then the last few dimensions are just the dimensions of the frame. And then you get the same information, the start of every frame and the duration of every frame for every frame in the clip. And we have different samplers. Here I presented the clips at random timestamp. You can also have clips at regular timestamp, so regularly spaced. And just like I said, we always have time-based API and index-based API, so you can also have the same clip samplers for, that are index-based instead. Okay, so a little tip about performance. By default, when you use TorchCodec and when you instantiate a video decoder object, what happens is here on the left. We do a scan of the video. The scan doesn't decode the entire video. We just read the entire thing. We read the packets that FFmpeg sends us. And these packets contain enough information for us to provide you with the accurate metadata that I just saw earlier. So that's how we correct the metadata from the header that can potentially be lying. And it also allows us to build an index of keyframes, which allows us to seek precisely where you asked TorchCodec to seek. I'm not going to go into too much details, but this scan is it's not super expensive. It's not like we have to decode everything, but it can still be expensive, and it scales linearly with the size of the video. So the longer the video, the longer the scan is going to take. You can avoid doing this scan if you explicitly ask for avoiding it, and sometimes it can really speed up the video decoder instantiation. You might be losing a little bit of accuracy into the seeking, and you might be losing a little bit of accuracy in the metadata as well. Most of the time, that's actually okay, especially if you're doing random sampling anyway. You don't actually care that you're not sampling exactly where you asked for. So we recommend using the approximate mode in general that will avoid the scan. And that potentially is going to be much faster. Streaming. So I said that you can pass as input local files, URLs, or anything, and you can also pass Python objects. As long as the object has a read and a seek method, it looks like a file. So it's a file-like. You can implement the logic inside of it as you want, and you can pass it to TorchCodec, and TorchCodec is just going to do what you ask it to. That's very useful because we can implement the logic we want to. For example, in the read function, we can download stuff from the web, from S3, from the Hugging Face Web, for anywhere. And we can just have a custom logic to download only the chunks that we want to download. So that's instead of having to download an entire 5 gigabytes video, we can just download only the bits that we are interested in. So that's very useful. And some libraries actually do that logic for you already, like FSPec provides a bunch of file-like subjects to download stuff from anywhere, S3 or whatever. Here I'm just passing it a normal URL, and this is how it would work. You just pass the file-like object instead of the path. And this is actually a lot faster doing this with FSPec than to pass the URL, the raw URL. Because if you pass the raw URL, you'll basically be downloading the entire video. Audio decoding. So we just released audio decoding as well. So far, I've only showed you how to do video decoding, but we do audio as well. It works exactly the same as video decoding. You instantiate an audio decoder object. You can get the metadata. There's no scan involved in here because we don't need to. And you can get all the samples, or just samples we're going to give in range, but really it's exactly the same, so I'm just going to gloss through it very quickly. Yeah, heads up, the PyTorch ecosystem is migrating. So we have already started deprecating the video decoders of TorchVision. They will be removed by the end of 2025. You are already seeing some warnings if you started using them, and we have raised warning in the docs. And the same is happening for Torch Audio. In Torch Audio, we have video decoders and audio decoders as well. We are deprecating these, and they will be removed. So you need to migrate as soon as possible. We will be doing the same with encoders, but before we remove the encoders, we will, of course, provide you with that, the same features in TorchCodec. The image decoders of TorchVision, for now, they stay in TorchVision. They are safe in there, so you can keep using them. They are not deprecated, but eventually in the future, I don't have any TA on this, but they will be moving to TorchCodec as well eventually, so that we can consolidate everything into TorchCodec. Our roadmap, so we want to be doing encoding, so it's the reverse process, right? You give us some raw decoded video frames, and we encode it into a nice MP4 or some stuff like that. Like I said, we want to move the image IO as well into TorchVision, but that's for later. A big feature request that's a lot harder than it sounds like is to allow you to run some pre-prog within the decoder. So FFmpeg or any decoder is capable of doing some pre-processing within the decoder. Like you can do resize, you can do cropping and things like that. And doing those transformations inside the decoder is potentially faster than doing them after the decoder, like by calling the TorchVision transform. The thing is, it's very easy to get discrepancies between your training stage and your inference stage. So if you were, for example, training with a resize strategy that involves bilinear mode and anti-alias, you absolutely have to do the same thing during inference. If you don't, you get some wrong results. So we are trying to expose this functionality in a way that doesn't allow you to shoot yourself in the foot and having silently wrong results. So it's coming, but we are trying to do it properly. And we're also trying to implement more backends as well. XPU is in the works with some Intel folks. Windows is probably going to come. And yeah, that's it. Let us also know what you need. Feel free to open an issue on the GitHub tracker. We'd love to hear whatever you need. And that's it. Thank you.